Hi, everyone. Thank you for joining my talk. My name is Yunxiang Zhang. I'm a PhD student at New York University, and I'm here to represent our team, including Nan, Connor, Gordon, and Chi, to tell you about our project, GazeFusion. As a brief overview, in GazeFusion, we propose a diffusion-based, saliency-guided image generation framework that incorporates the data priors of human visual attention mechanism into the generation process, such that the generated images can attract viewers' visual attention in desired, predefined ways. Talking about image generation, or more generally, content generation, I believe many of you have heard of the recent AIGC boom and the powerful models behind all this progress, diffusion models. Given a detailed text prompt like this, it's a real world where reality and illusion blend together, and so on. State-of-the-art image diffusion models can generate, in a flash, high-quality images that faithfully represent the content as described by the text prompt. While this kind of text guidance is very flexible and user-friendly in terms of describing the desired image content, the control it provides is rather coarse in general, and sometimes it can be very tricky to obtain the desired precise control effects over the generated images. For instance, it's a horrible task to adjust the position and orientation of the sign here or the body pose of the squirrel here using text prompts only. To address this issue, researchers have been exploring additional formats of control signals to enforce layout guidance. For instance, it's now possible to use caption bounding boxes to precisely control what image content is generated where, such as the bouquet of flowers and the vase in this generated image. This kind of layout-like guidance has been successfully demonstrated with a variety of control signal formats, including depth map, line drawing, body pose, semantic map, etc. This is all very cool and effective, but we're not just generating images for fun, right? Eventually, most of this generated visual content, if not all of them, will be consumed by human users. So here comes the question. Is it possible to know beforehand how the generated images would be viewed by the target users? Or maybe even better, could we design and control the way users would distribute their visual attention within the generated images before the generation even happens? Before answering this question, let's first look at an example. If you were sitting in front of a 27-inch computer monitor and were shown such a full screen image for a few seconds, which image regions would you pay more attention to? For me, I might first take a glance at the herd of cattle in the lower center region, and then shift my eye gaze to this somewhat eye-catching farmhouse. This kind of behaviors is very common and natural, as our visual system has developed to be more sensitive to high contrast, semantically rich, and less frequent content in the foreground. In other words, such image content is more salient and attracts more visual attention from viewers. Now, if we ask many people to view this image for a short period of time and aggregate their eye gaze scan paths together, we can get some generalizable statistics of its saliency distribution. This distribution is visualized here as a color-coded saliency map, where warmer color indicates higher saliency. Of course, human visual attention mechanism operates in a very complex manner, far more complex than what can be properly described by a simple analytical model. As a matter of fact, there are a lot of factors that can induce visual saliency than what we just saw. To name a few, prior research has evidenced that low-level image features such as color, contrast, orientation, layout, and spatial frequency, as well as high-level semantic information such as objects, text, faces, and body gestures all contribute to visual saliency. Here, we show a few examples of such concepts. The grayscale plots here visualize the saliency maps of their corresponding images, and a brighter color indicates higher saliency. Now we can go back to the previous question. How do we design and control the way users distribute their visual attention within the generated images? Our answer is to exploit saliency maps as a proxy for guiding the image generation process. Specifically, we instill the data priors of human visual attention encoded in a diverse set of saliency maps into the image diffusion models for attention controllable image generation. Given a text prompt and saliency map pair, our saliency-guided model can generate images that not only contain the content as described by the text prompt, but also attract users' visual attention toward the desired image regions as emphasized by the saliency map. But how do we achieve this? Since the scale of existing image datasets that provide paired eye tracking data is typically below 10,000, and thus too limited to support decent generative learning, we instead use Microsoft COCO as the image source and resort to a learning-based saliency predictor, which has been trained on real human eye tracking data for extracting the corresponding saliency maps. We also use a language model to caption these images for paired text prompts. This results in a total of about 560,000 text, saliency, and image pairs. We then attach a control-net module to the encoder and middle blocks of a pre-trained text-guided only stable diffusion model to inject the saliency guidance into the diffusion denoising process through saliency to image translation learning. The supervision is enforced in the image space by computing the loss between the generated image and the ground truth. At the deployment stage, our model first randomly samples a noisy image as the starting point, then conditions the image generation process on the user-provided saliency map and text prompt, such that the image features and semantic content in the generated image would trigger similarly distributed viewer visual attention to the desired saliency distribution. Here are some examples of our saliency-guided generation. You can see if we couple the same simple saliency map with different text prompts, the model is capable of generating diverse images that exhibit roughly the same saliency distribution. For instance, you can see how the model manipulates the given material texture to satisfy the desired saliency distribution, like the round wood grain and carving here, the circular shape and changing spatial frequency of the ripples here, and the outstanding color and contrast of the images here. And very interestingly, the direction of the fur in this image. And of course, the layout of the salient foreground objects in these images. And here's another slightly more complex saliency map combined with several text prompts. Actually, this saliency map contains more than just this bright dot, but it might be a bit hard for you guys to see the non-black scattered saliency around this area here. And that's also why, in addition to the main subject in this area, we also see a bunch of stuff generated in this area. So even if some areas in the saliency map are visually insignificant to human eyes, they may still have a significant impact on the model, and thus the generated images. Therefore, it's typically not a good idea to inspect or analyze saliency maps by eyes. And among these images, I find this column particularly interesting. You can see how the model adjusts the visual saliency in this area by adding a cherry here and adding a different color filling and also more filling here and rotating the macaron to be differently oriented from the others here. And we also tried combining the same text prompts with different saliency maps for generation. So here are some examples showing the same semantic content manipulated in different but legitimate ways to follow the required saliency distribution. After seeing all these generated images, you can tell that our model can flexibly apply a combination of various image features and semantic content during the generation to steer viewers' visual attention. And as I just said, it's not accurate to visually inspect saliency maps. Obviously, neither is it accurate to visually judge the saliency of generated images. So, to quantitatively evaluate our saliency-guided approach to attention-controllable image generation, we conducted an eye-track user study on the model-generated images to analyze its attention steering performance. Specifically, we recruited 20 participants for the study and used a Tobii eye tracker to record their eye gaze behaviors while they browse through a sequence of generated images with a 5-second viewing duration enforced on each image. In addition to our saliency-guided model, we also included a text-guided only model and a caption bounding box guided model for attention steering performance comparison. In total, each participant performed free viewing on 150 images, with 50 images generated by each model. The video clips shown here illustrate our experimental setup, and the eye gaze data collected from a participant. Here are the results of 7 images randomly sampled from the 50 image set for the text-guided model. The first row shows the generated images. The second row shows the empirical saliency maps, or put it another way, the achieved saliency distributions, which were computed by aggregating all participants' eye gaze scan path on each image. And finally, the third row shows the desired saliency distribution. The yellow numbers associated with each empirical saliency map here measures its correlation with the desired saliency distribution. While the numbers shown here reveal a rather weak correlation between the two sets of distributions, and thus a pretty weak competitor on this task, this model should be considered more like a strawman condition for establishing the baseline. And here are the corresponding generated images and empirical saliency maps for the captioned bounding box guided model. You can see that after constraining the appropriate semantic contents to the desired image regions, the achieved saliency distributions now align much better with the desired ones. However, the control over image details provided by this kind of layout guidance becomes limited in images with complex content, and further fine-grained enumeration is clearly not scalable. Besides, visual saliency is not just about the layout of the semantic content in the image. By contrast, our saliency-guided model offers a more accurate, efficient, and generalizable approach to manipulating viewers' visual attention over generated images. Here you can see from the numbers that our model consistently outperforms the bounding box baseline by a large margin. And this is also evidenced by 5 commonly used saliency similarity metrics over the entire image set used in our user study. Now that we have the power to generate images that steer users' visual attention through pre-designed saliency guidance, what kind of interesting things can we achieve? Actually, if we can drag viewers' attention toward desired image regions, a natural follow-up question would be, can we instead shift their attention away from unwanted image regions? To answer this question, we crafted 3 saliency maps that basically only contain completely black or white regions, and the differently sized black regions indicate where viewers' visual attention should be shifted away, or put it another way, completely suppressed. As you can see from these examples, the model tried to remove anything that would induce visual saliency from the suppressed regions while generating overall plausibly composed images. We call this kind of complete attention shifting in certain image regions absolute suppression. But there are also times when we don't really want to make certain image regions completely unattractive, but only reduce their saliency compared to some other image regions. This can be achieved by adjusting the saliency guidance in different image regions to show a relative intensity difference, like what's shown in these 2 saliency map pairs. Very interestingly, here the model not only positions the 2 persons to the 2 salient regions here, but also makes the person in the more salient region here face the camera, and the other person turn her back to the camera and slightly out of focus. Similarly, here you can see the clear difference in terms of saliency between the 2 bottom image regions. We call this kind of relative attention adjustment in different image regions relative suppression. When it comes to designing the saliency guidance, we need to be aware of a very important point. When the saliency guidance is incompatible with the accompanying text prompt, our model may generate unnaturally looking images that contain severe artifacts, such as the disfigured bare bodies shown here. To address this issue, we developed an interactive saliency design system that proposes corrections when necessary to ease users' trial and error effort in crafting high-quality, prompt-compatible saliency maps. As you can see on the bottom row, after optimizing the tentative saliency map to be more compatible with the text prompt, our model was able to generate naturally looking baby bears without artifacts while maintaining the desired saliency layout. Due to the time constraint, I'm not going to go into the details of our implementation here. Please refer to our manuscript for more information on this. Using our saliency-guided model, one can also perform display adaptive generation to optimize users' viewing experience under varied display and viewing conditions. More specifically, based on the specific viewing condition, including the size and aspect ratio of the display and the user's viewing angle and distance, one can adapt the user's visual attention distribution by adjusting the saliency guidance, such that the main image content is located within a reasonable field of view for the users. This can help improve the visibility of important image content, and users also won't need to shift their eye gaze or rotate their head as often due to peripheral viewing. Here's an example of making the image content remain in a comfortable field of view after switching to a wider field display. To sum up, in this work, we propose a saliency-guided framework for viewer attention controllable image generation and demonstrated 3 potential applications. This is really just a first step toward human-centric control over generative models, and there are many fascinating future directions to explore. For instance, the factors that trigger visual saliency are very diverse, including low-level features, mid-level structures, and high-level semantics. Currently, our model doesn't differentiate between these underlying causes. So integrating saliency models that target different levels of saliency-inducing factors may shed light on multi-level, fine-grained saliency-based control. And in addition, the natural next step would be to extend our approach to saliency-guided video generation. We actually had a preliminary experiment on this by combining our saliency-guided image generation model with an off-the-shelf zero-shot video generation pipeline to generate temporally consistent video frames with spatial temporal saliency guidance. However, as you can see, the resulting generated videos often exhibit some unnaturally looking temporal artifacts, like with this cat. So introducing an explicit temporal module to constrain the temporal correlation between adjacent frames may further improve the generation quality. So yeah, that concludes my talk today. Thank you very much for attending, and I hope you enjoyed it.